So, hello everybody. In this presentation I will discuss what we have called the temporal Arago spot and that we have observed in optical fiber. So the experimental work has been done at the Laboratoire Interdisciplinaire Carnot-Bourgogne in Dijon, in France, by myself, Christophe FINOT, and it has been realized in close collaboration with Hervé Rigneault from the Fresnel Institute in Marseille, also in France. So my presentation will be organized as follows. I will first recall what is the Arago spot and the basis of the space and time duality. I will then explain how we can expect to see this Arago spot in optical fiber, and I will also show the analytics of this waveform. Then I will describe our experimental setup and the various observations that we made. And before conclusion, I will discuss the impact of the Kerr nonlinearity that affects the pattern that we record. So let us first recall what is the Arago spot. The Arago spot is closely linked to the Fresnel theory of diffraction. Indeed, when Fresnel presented his works about wave optics, there has been very strong discussions between two French scientists, Arago and Poisson. Arago was pro the theory of Fresnel, and Poisson was strongly against his theory, and one of his arguments was that if we observed what happens in the shadow of circular apertures, the Fresnel theory predicts a bright spot, and this is for him stupid, because there should not be any light in the shadow of an opaque screen. So for him, it will lead to say that the theory proposed by Fresnel was completely wrong. Arago proposed to make the experiment, and the experiment showed that at the center of the shadow there is a bright spot that appears. So here we have a very nice example of an experimental crucis, and here we have an example photography of this experiment where we see here the bright spot that can happen at the center of a circular opaque screen. So this is a very important experiment that has been done in 1819, so 200 years ago, and this has motivated for us this work. So now let me explain the analogy that can be drawn between diffraction and dispersion. Imagine you start from the easiest wave that we have, so a monochromatic wave and a plane wave, so a single frequency, and in the Fourier space just one component about the spatial frequencies. If you limit your wave, then you will in the spatial domain increase your spectrum, and with the propagation it will lead to diffraction. So here this is a limitation in the spatial domain. Now if you make a limitation in the temporal domain by using a short pulse, for example, then you will broaden your frequency spectrum, and given the propagations that you have, you will induce dispersions. So here we will restrict to the cases where the broadening of the spectrum are quite narrow, both in diffraction and in dispersion. And what we can see is that the governing equations are very close. We can see that we can draw an analogy between the two main equations of propagation. We just have to change a few variables, and we can make a table. In both cases, we have the same propagation variable. We just have to change the coordinate that we consider, x, the transverse coordinate in the case of diffraction, and t, the time in the case of dispersions. And we'll have also to change the corresponding variable in the Fourier space. So the analogy is quite simple to write, and with this analogy you can find that we have similar phenomena in both regime. What we call the far field, the Fraunhofer regime in diffraction, we also have it in the field of dispersions. We can have in the spatial domain a lens. This is a quadratic phase on the transverse coordinate. We can imagine a lens in dispersion in the temporal domain. It will also be a quadratic phase, but this time on the temporal domain. And diffraction, dispersion, both induce a quadratic spectral phase. All this is linked to the propagation equations. So it is quite well known, and if you want some more details, you can go to these different reviews that are very well made. And it has also practical applications. Here I've only mentioned a few of these practical applications. Here is the dispersive Fourier transform. It has been used also to make temporal gratings. Application to reproduce the Talbot effect in the temporal domain, and we can use also the temporal lenses to make temporal imaging and very nice things to magnify temporal events. What we are interested in today, this is the equivalent of the Arago spot. So our analogy, it only works in the 1D case. So we will not be able to consider in the temporal domain something that is fully equivalent to a circular screen. So we will be limited to a 1D configuration, and in this case, what we will consider, this is a linear opaque stripe. So here we have the stripe, and what we see, this is that we have a growth at the center of the shadow of a bright spot that is quite similar to the Arago spot. Here, this is restricted to the 1D case. That means that it will not be as intense as the spot we observed with a circular opaque screen. So here is a nice photography of such a spot. We can see here at the center the equivalent of the Arago spot in the 1D case. This photography is from the Atlas of Optical Phenomena from Gagné, Poisson, and Chair. So very nice photography. And we can quite easily find the analytics for this waveform. And what is usually taught to the students, this is the shape of the diffraction by a straight edge. Here we have, in fact, two straight edges. So we have to add the diffraction pattern of the two edges, but we should not add them incoherently. So we should not just add the intensity profile. It will not reproduce the bump that we have at the center. We have to add the fields. So the two contributions will interfere, and it will be this interference that will lead to the bump that we observe at the center. So this is here really an interference process between the diffraction pattern generated by the two edges. So for this, to describe the interference pattern of an edge, let me just recall that you have to play with the Fresnel integral C and S, and when you write things properly, you will obtain analytically the field of your shadow, and it will work very well with the numerics. So what we want, this is to observe all this not in the spatial domain but in the temporal domain. So we need to have a dispersive medium, and the medium that we have chosen, this is an optical fiber. Why have we made this choice? Because the optical fiber is close from the ideal medium. If we use a single mode profile, the spatial profiles of light will be preserved. It is single mode, it will not change, so there will be no effect of diffraction. Thanks to the very low level of losses of the optical fiber, we can propagate the signal over several kilometers without nearly any losses. what is also very stimulating, this is that we can have access to all the devices from the telecommunication industry. So we have very good photodiodes, very good equipment to characterize the device. And finally, with optical fiber, we can also play with the level of dispersion, and we can have fiber with a dispersion that is normal or anomalous. So we have here some freedom on the sign of the dispersion coefficient that is used in the propagation equation. And as we will see when nonlinear duality will be induced, it will change a few things. So here are the results we obtain theoretically in the temporal domain when we consider the evolution of the intensity profile, but we are also interested in the evolution of the phase profile. And what we can see, this is that there is a phase shift between what we have at the center of the shadow and what we have at the outside of the shadow. So we will try also to characterize it. Regarding the intensity profile, we see that there is the growth of the Arago spot, and there are also some very strong oscillation that appears near the edge of the shadow, and this oscillation deviates from the center. So let us now see if we can reproduce all those features experimentally. So here is the experimental setup that we use. It seems to be quite simple, and it was our goal. So we start from a continuous wave, and in order to generate the initial profile that we want, we just use an intensity modulator that is driven by an electrical pattern generator, and the pattern that we use has a repetition rate of 2.5 GHz. Then this pattern will propagate in a series of optical fiber. So we use the most standard fiber that exists in telecommunication fiber. This is the standard SMF28 fiber that has an anomalous dispersion. So we have used different lengths of spool. We have combined the different spools. So we were with this able to characterize the propagations for very different lengths of propagations. And at the output, we were able to characterize the resulting signal both in intensity and in phase using a complex optical spectrum analyzer. So what was quite important here, it was the initial signal that we send. Here it is plotted in blue circle, and what we see, this is that it is not perfectly rectangular, but the edges are very sharp. So we are quite close from the ideal initial condition that we have considered for the analytics. Here, in fact, we have something that is closer from a super Gaussian shape. We can see that also the shape in the temporal domain is quite symmetric, that we have a very nice extinction ratio. And if we go to the spectral domain, we see that the spectrum is also symmetric, and that the optical signal-to-noise ratio is also very nice. It is more than 60 dB of optical signal-to-noise ratio, so a very clean initial signal. So let us now see what we have at the output. So here is the signal for 3 different lengths of propagations, and we see the different features that we have mentioned previously. So we have at the center the Arago spot, which level progressively increase upon propagations, and in the edge we see the oscillations that are moving from the center of the waveform. So we reproduce quite well what we were expecting, and we can make here the comparison between our experiment and the results of numerical simulations, and we see that the agreement is excellent. The experiment can be closely reproduced by numerical simulation that take into account the real initial waveform that we have sent into the fiber. And we can also do the same work regarding the phase that is provided with our complex optical spectrum analyzer. And once again, we see that the experimental results are fully reproduced by numerical simulations. The agreement is again very good. And we see here, we clearly reproduce the phase shift between the central part of the waveform and the part outside the shadow. And if we look more closely to what we have at the initial time, at t equals 0, we can see that the experimental result plot here with blue circle are closely reproduced by the numerical simulations and qualitatively reproduced by the analytical trends that use a perfectly rectangular waveform. The analytical result is not perfect for short propagation distances. So let us now discuss the impact of nonlinearity. Let us first recall that for standard diffraction, here I have taken the example of some result obtained by the group of Jason Fleischer in diffraction in a Kerr medium. What we see, this is that the diffraction pattern here of a perfect edge is affected by the nonlinearity. The fluctuation becomes higher and higher here. This is an example in the spatial domain with diffraction. So we try to see if there is also such an effect in the case of dispersions. So we have taken into account the nonlinear effect that exists in an optical fiber. And the nonlinear effect that we have, this is a Kerr nonlinearity. So the propagation index will depend on the intensity of the field, and to take this into account, we just have to add a term to our propagation equations, and it will lead to the nonlinear Schrödinger equation, which is known to be very efficient to describe the propagation in an optical fiber. So here we have to separate two cases. The case where the dispersion is normal, so beta 2 is positive, it will lead to a defocusing nonlinearity, and in the other case, in the case of anomalous dispersion, the nonlinearity will be focusing. So we have changed our setup. We made some small changes. We have inserted an Hervé absorbed fiber amplifier to increase the level of the signal. So with this we can reach much higher peak powers to stimulate the nonlinearity. The drawback of handling high powers, this is that it may also induce some Brillouin scattering, and this Brillouin scattering will be very detrimental for the observation of the signal we want to analyze. So to mitigate this Brillouin backscattering, we have used a phase modulation here that will increase the line width of the initial continuous wave laser. The drawback, the cost of using this phase modulator, this is that we will not be able to use our optical spectrum analyzer anymore, so we will not be able to have access to the phase pattern anymore. We'll just be able to record directly the signal in the temporal domain using an electric sampling oscilloscope. And here are the results we obtain for 3 different levels of power. What we see, this is when we compare the propagation in the fiber with low nonlinearity, so in the linear regime, we see that the Arago spot, in the case of the focusing nonlinearity, is higher that what we obtain when we increase the power. On the contrary, the side lobes, not the side lobes, the ripple that we observed near the edge are significantly increased by the focusing nonlinearity. So here we have a strong increase of this fluctuation. And this is exactly the opposite in the defocusing case. What we have in the defocusing case, this is that when we increase the power, we see the Arago spot that increases, and the ripples that we observe near the edge tends to decrease. So very different behavior according to the sign of the dispersion regime. And once again, we can compare our experimental result with the result that we have using a numerical simulation of the nonlinear Schrödinger equations, and we see that the agreement is excellent. We clearly see here the strong influence of the average power on the dynamics. And here, if we are just interested to what happens at the center of the pattern, we say that according to the dispersion regime that we consider, so on here the left, this is the anomalous dispersion, and the right, the normal dispersions, we may have very different behavior with opposite trends regarding the level of the Arago spot. So it is now time to conclude. So to conclude, we have provided a demonstration of the temporal analog of the 1D Arago spot, and to do this we have used optical fiber. Our experimental results, both in amplitude and in phase, are in excellent agreement with the theoretical and analytical predictions, and the regime of dispersion strongly influences the patterns and the intensity of the Arago spot. So those are the three main points that I can say to summarize our results. You can find all the details in the publications that we made in Journal of Optics, when you will find all the details of the analytics. And our motivation, once again, it was to celebrate the result of Fresnel that have been obtained 200 years ago. So thank you for your attention.